What I would like to talk today is information, and actually Shannon legacy, and to explain to you why we need to go beyond Shannon and to go to something that we'll call science of information. And at the end, I will present few technical results. So let's start with Shannon. In 1948, he wrote the paper, A Mathematical Theory of Communication, and the digital age began. In this paper, he did three things, at least from my perspective. First, he gave us the first definition of information, a rigorous definition of information. And I will spend some time trying to explain what it is. One thing that he actually did, at this time he said that the semantic aspect of communication is irrelevant for information. Let me explain why he did it. If you try to understand the traffic of trucks of I-96 or I-65, you do count trucks. You really do not care what do they carry, tomatoes or potatoes. But, so semantics doesn't matter for traffic, but it matters, of course, for the recipient of information. So one thing is information, and I will try to explain a little bit and philosophize a little bit what information is. Then, he gave us a theory, a mathematical theory, a fundamental limit for two things, storage and communication. He told us what is the minimum number of bits that you require to actually represent a file, which is the storage. And then for communication, he told us how many bits do I need to transmit in order to communicate in a trustful way, in a reliable way. With this mathematical theory, with mathematical theorems, he paved the way for today's advances in communication, incredible advances in communication, from CD, iPod, DVD, and so on, to internet. And he also gave us design techniques such as, for example, universal data compression, which actually can be used in biology. Okay. So let's go and let's try. So there are three things on this slide that I want to concentrate. Information, fundamental limit for compression and data transmission. I will try to give you in a gradual way and try to show you what Shannon did, up to some Greek letters that we skip. So let's talk about information in a more general way. And let's philosophize a little bit. First of all, von Weizsäcker, he did agree that semantics, meaning, doesn't matter. And by the way, Shannon made the right assumption 50 years ago, but we cannot go anymore without actually semantics and knowledge. And I will try to explain why. But von Weizsäcker said that information is that produces information, and that was in biological context, and which is understood. Let me explain this by going to Richard Feynman, a great American physicist, who in a simpler will explain what does it mean. Information is not simply a physical property of a message. It is a property of the message and your knowledge about it. Let me give you an example. If you just submitted a paper to a conference, and you are waiting to know whether you get acceptance or rejection, then an email comes with the subject, your submission. The email is very long, but only three words matter. I regret to inform you, or I'm pleased to inform you. The rest is, that what it is there. So that's why prior knowledge does matter. Now let's stay in physics. And in the 80s, John Wheeler, another great American physicist, when quantum mechanics actually becomes more and more popular and better understood for most of us, he came up with a statement, it from bit. It's a famous statement, which means, it here means physical real world. Bits here means information. He basically claimed that reality comes from information. The reason that he did say is, let's take a photon. This photon, until you measure, does not exist, some will tell you. And once you measure it and ask the question, yes or no, this is for the first time that you realize reality. Some disagree and actually reverse saying bit from it. And Anton Salinger, he's an Austrian physicist, the first one who did teleportation. He actually said that reality and information are two sides of the same coin. So this is a very general discussion by information. And at some point, I will go lower it to what actually Shannon did for us. So at least, I hope I convince you that information has two flavors, the relativity, which is related to activity, and rationality, knowledge of the recipient. Information has also temporal, timeless aspect, which is the hardest to do, and Shannon actually completely ignored it. But we all know that information is related to time. If information arrives too late or too early, it has much different value. That's why we say time is money, yes? In economy, information, timeline information is crucial. And the same in actually biology. If your living cell does not react to outside symptoms in a given period of time, it might be actually lethal, it may die. So a few years ago with my colleague, trying to understand it and going into actually trying to understand philosophy a little bit between information, we come with a very general definition, which is pretty much useless for most engineers. But let me say it. A piece of data carries information if it can impact a recipient's ability to achieve the objective of some activity within a given context. It is useless because it's too general. It's too narrow for philosophers, but for engineers, it's too general. So let me give you my understanding of information that actually could be acted upon. I claim that information is a measure of distinguishability. And let me explain this to you. I have somewhere in my pocket coins, okay? If we all agree that all my coins are the same, if I pull one coin and show it to you, I'm giving you 0 bit of information. You are not learning anything. Do not surprise you at all. But in fact, I do not have all coins the same. I don't know if I can pull one of this. But I have actually different coins. If I pull one of this, and let's say it's French franc, I'm telling you something about something new. If I have, for example, let's say 10 euros in my pocket in 1 quarter, and if I pull out this quarter, because it's very unlikely to happen, gives you more information than if I just pull a Swiss franc. So you can see that when I have distinct coins in my pocket, when I show it to you, distinct signals that you learn something. Another non-trivial example is basically the question that Boltzmann asked in 19th century. This is, by the way, where the information for the first was somehow defined, because this was the time that Boltzmann defined entropy, which is at the background of all information. He basically was asking himself a question: how many distinguishable distribution of gas molecules are there? And he asked which one is the most likely to occur. So I will claim that information is a measure of distinguishability among signals, about messages that you saw, values, and so on and so on. I think I'm ready now to go to Shannon, what Shannon did. Shannon defined statistical information, how the reduction of statistical ignorance or statistical uncertainty. How much do I surprise you when I show you something, when you see one of the many messages? And if the message that is very rare, when it occurs, it tells you more than a message that is very frequent. That's why he actually related information to probability of a message. E is an event, just pulling a coin from my pocket. So, but that's not it. Probability is probability. Information is something else. Because for information, in order to actually to learn something about the event, you have to ask questions. Let's say if I have 4 coins in my pocket, and I pull one of this, the question that you will be asking is yes or no question. Is this coin from Europe or is this American coin? If it is from Europe, it is Polish zloty or it is euro. So the number of questions, binary question, yes or no, that you're asking for an event, that's what Shannon defined as information. So that is minus logarithm of the probability of the event. That's what he's called self-information. If you average over all events, like we did here, we are getting entropy. There is Shannon entropy, which is related to Boltzmann entropy, but that's what it is. Finally, when you have 2 events, when you are transmitting some signal X on the other side and receiving signal Y has its uncertainty in the entropy, but it's reduced by the fact that I learned something from X. This difference is called the mutual information I will use at some point. The last thing that I want to tell you, that information is not absolute. If I pull a page from a book and I ask you how much information is there, you won't be able to answer it, and I tell you that, you can count the number of different symbols, or you can count the number of different words, or you can count the number of different shapes. So there is no one definition of information. Okay, I'm going more into what Shannon told us. And here, I start with an example. Remember, I have 2 other things to tell you, not only what is information, but actually how to act upon it with finding the shortest description and transmitting. So here's an example. I want to transmit 8 messages, and the probability of these messages are from 1/2 to 1/64. 1/2 is very likely to occur. 1/64 is not very likely to occur. I want to transmit it with the smallest number of bits. So what I do, for very likely event, I will give a very short description. For very unlikely event, I will give a very long description. Actually, this is the code, compression code called source coding, of the message they want to transmit here. If you compute the average code length, it turns out it's 2 bits. But there is a surprise. It turns out that entropy of this source is also 2 bits. And when Shannon told us that you cannot compress more than the entropy of the source, the expected value must be greatly equal to that, the entropy, not much more. So let me go a little deeper in this and actually try to establish this fact in a little better way. So what was the most important about Shannon, and I like the spirit of Shannon, was to ask fundamental questions and then do simple mathematics to answer it. And here's the first question that Shannon asked. How many bits do you need to describe a file? What is the minimum number? What is the minimum description of a file? And here how Shannon answered it. He said, I need no more than the entropy of the source. You will see this figure in a second when I will explain to you how he proved it, basically by flipping a coin. So this is the first result. If you do not need to recover exactly the signal, then there is something else called rate distortion, but I'm not going to go into it. The second question, which is even more profound, that he asked is the following. When I transmit bits between 2 points, fixed points, let's say, how many bits I can transmit when I know that between these 2 points, there is a channel that is actually noisy and corrupt. So let's see. Let's assume that up here at the input, I have n binary bits, 0 and 1. How many different messages I can have? 2 to the power n, because bit can be 0 and 1. So maximum number of bits that I can transmit is 2 to the power n. But if I do it, when I transmit it, and this channel introduces an error and corrupts 0 to 1 and 1 to 0, then with relatively high probability, I can actually make a mistake, and this is not good. So what Shannon say? Shannon says the following: I'm not going to transmit all possible inputs. I'm going to transmit less. How many less? 2 to the power n times some small number r, let's say 1/2. So what I do, I create a space in the space of all signals, and actually I make enough space that when I make a one mistake, one error, I still can recover the message. It shouldn't be too much surprise to you. I'm speaking to you in English with good Polish accent. You still understand me, I hope so. Why? Because there is enough redundancy, robustness in the language, and that's what Shannon codified in the mathematical formula. He basically told us that I can transmit with the rate r up to the capacity, certain number, that is a theoretical result that for the last 50 years, engineers are trying to build transmission devices that reach this capacity. And they do not chase unrealistic goal because we cannot transmit more than the capacity. Okay, I finished with a hand-waving proof of this result, at least one of this. I told you that his result about compression is about flip coining. Okay, if I take a coin and flip it 1,000 times, what you can expect? You can expect that you have 400 heads, maybe 450, maybe 500, maybe 600. It is very unlikely that you will have 1,000 times a head, okay? It's very unlikely that it happened 900 times. So if this is the space of all possible sequences of length and binary sequences, there will be some that are typically to occur. With the bit flipping, you will have the number of bits between 400 and 600. The rest can occur, but with a very, very small probability. So here what Shannon said, okay, and that is his proof of his first result. I'm going to take these typical bits, sequences, and I compress it, but they're taking logarithm of the probability of this typical sequence. What is this typical sequence probability? It turns out, it's easy to show, it's 2 to the minus n times entropy rate. So if I take log, I'm basically getting entropy of the source. All the other sequences, I'm not going to compress. I'm going to send all of them as they are. But because there are so small probability, I basically achieve the rate that I wanted, the entropy rate. That hand-waving proof of Shannon's first result. Very briefly, because Shure is looking at me, let me tell you how he proved his most profound result about the compression. He gave a proof that is completely unrealistic. You cannot build an algorithm on it, but this gave us the basis to actually create code that achieve it. He says the following: when I receive a signal that is corrupt inversion of x, and from this x, I have to guess which x was transmitted, he says the following. Again, do flip coining, but now you are flipping two correlated coins. And he's saying, okay, when I receive y, the x that is transmitted will be the one that, as a pair, x and y together are typical. If there are more such a pair, you declare error. And he was able to prove that this so-called random coding approach, which is basically a theory proving not realistic to construct, he achieved the capacity of the channel. So now you know what Shannon did. And finally, I needed later for the third part of my talk, if you have a very simple channel, you have a stream of bits, any stream of binary bits that you want, and 0 is corrupted with probability p to 1, 1 is corrupted to 0. What is the capacity of such a channel? It's 1 minus entropy of the noise. I will come back to this in the third part of the talk. So Here you have some idea what Shannon did. He gave us foundation of reliable communication. How to recover data on the receiving side in a trustful way. But the question is, what we should do now when actually we not only communicate, most of you, what you are doing probably during the day is surfing on the web. Yes, you are querying database, you are trying to receive an answer. So information nowadays is not only communicated, it's acquired, organized, managed, valued, represented, analyzed, and so on and so on. We need to go beyond original Shannon theory of reliable communication and build something that we try to define as a science of information, or you can call it a theory of information. By the way, Shannon never called his theory information theory. He could call it theory of communication, but not of information. By the way, like Shannon, and that's the spirit of Shannon, asking questions is as important as actually trying to get an answer. And Shannon's contribution was building the model and asking the question. So paraphrasing Cantor, in science, the art of proposing a question must be held of high value as also answering it. So what we want to do, and the Science of Information Center was mentioned here, we would like to extend Shannon information beyond the original goal. So it has application from biology to economy to big data, name it, because information permeates every corner of the universe. We in the center decided that we concentrate on few aspects of information: structural, temporal, spatial, and semantics. And semantics is very important. And we try to understand this aspect of information in a dynamic environment of a wireless network, let's say, with limited resources. You cannot talk on your cell phone for too long because your battery dies. The same, your living cell cannot perform every task because it has limited energy. And so we want to try to understand the dynamic information in the limited environment and these three aspects. So if you ask me, what is the challenge for the next 10, 20 years? I think with the data deluge we are dealing every day, we need to bring the paradigm from data to information to knowledge and try to understand each aspect of it. Knowledge here understood in a very narrow term, actually information and action. So information, I try to give you a definition, the measure of distinguishability. Once you extracted information, you have to act upon it and gain knowledge. So if you ask me a few questions, and Anand helped me with formulating them, I would say the question about data are the easiest one. The question about information, we are there. But the question about knowledge, we are not there. So what kind of question about data? 20 years ago, all the data was in the form of text. Textual data, it was easy to deal with it. Right now, on the web, you have audio, you have visual data, name it. And in biology, you have many different data coming together. You have network of enzyme communicating, protein network. For each of this enzyme, you have a gene ontology, which can be represented, what we call DAG, directed acyclic graph. There are trees somewhere there, and many others, different data structure. We call it from sets to trees to graphs and others. So we have to deal with the multimodal data structures and try to understand what is the shortest description of this different data coming with different underlying probability. And we don't know this probability, okay? A harder question is, okay, once I know what the data is, let's ask how to even compress it, how to extract information from this, how we can do it in a universal way without knowing actually underlying distribution. The hardest question is about knowledge, because we know that information starts somewhere, has causes and consequences. Sometimes we see consequences, but how we can learn about the causes in a reliable way? So these are our 5-year project for our center, and actually last year when I presented it for the renewal panel, that was exactly our paradigm, going from data to information to knowledge. So that's what we want to do. Okay, I'm seeing I'm okay with time. So let me introduce some Greek letters now and tell you this award is for something, not just for talking. So let me just give you some technical contribution that together with my collaborators and with students, I was able to do it. So you remember when I show you this binary symmetric channel, a stream of bits 0, 1 coming in, and then I was asking how many of them I can transmit in a reliable fashion over a channel with noise. The problem is that the stream of bits 0 and 1 is never unrestricted. It always has some restrictions. So let me give you 2 examples. In recording, old-fashioned magnetic recording or new DVD, CD, or Blu-rays, in order to get a good quality of the sound or audio, you have to be careful how many bits you want to transmit. Between any 2 signals, you have to put some zeros silent, but not too many, not too few, not too many. Why? Because you can lose synchronization. So for this kind of devices, your input is actually restricted to something that is called a decay sequence. A decay sequence is a very simple sequence, binary sequence, such that between 2 ones, you have to have at least D0 and at most K zeros. This is called a decay sequence. And it has application here. Second, we are collecting enormous amount of data from brain, and this brain are basically spikes, which are ones. And between the spikes, anatomy of brain require a silent period. So between 2 ones, I have to have at least 2 few zeros. This is another area that decay sequences fall describe quite well, much better than unrestricted 0s and 1. So here's the channel that I showed you before. My error of probability is a binary channel. 0 can be corrected to 1, 1 could be corrected to 0 with pretty epsilon. The only difference is that my input right now is not unrestricted bit sequence of bits 0 and 1. Now I will require that this sequence satisfy the constraint of decay sequences. And the question is, what is the capacity of such a channel? Do you remember, without restriction, the capacity of the channel was trivial, 1 minus the entropy of the noise. What about here? Okay, here's the problem. This input, by the way, is not any memoryless. When I see 1, I know I have to, in order to see what is the next bit, I have to know the last k bits. Because if the last k bits were 0, I have to put 1. So the input here has a memory. And this is called Markov processes of order k, because next bit depends on the last k bits. Okay? Here's the problem. When I put an input, the Markov sources of a noisy channel, the output is a very ugly process. It's called hidden Markov process. And the question that was formulated by Shannon 50 years ago was, okay, what is the capacity of such a channel? And for 50 years, we have been struggling with this. And then I was lucky with my colleagues actually to observe a few things. So first of all, observe that the mutual information, again, is entropy of the output minus conditional entropy. This conditional entropy is nothing else but noise. So it's entropy of the noise. I have to understand entropy of the output process, which I just explained to you. is a hidden Markov process. What is this entropy? This is a basic question. Yes, but it's a difficult one. In Blackwell in 56, tried to compute it in and gave a very long useless formula with many integrals. We contributed to the node by giving another useless formula and represented this as a product of random matrices that led to top Lyapunov exponent, which is uncomputable, also actually hard computable problem. But then we realized one thing. The probability of error is small in most of the advance. And then we were able to make a progress. We actually then show that the entropy of the output is the entropy of the input minus corrections. These corrections are of epsilon log epsilon order and epsilon. And we can compute this. And in fact, for a 0-1 sequence, which means between two ones I put 1, 0 or non-zero, which has this matrix, transition matrix probability P, we were able actually to compute it. Knowing this, we were at home because then we were able to show that the entropy of such a system is entropy without the constraint plus the correlation. This P max here is the transition matrix that optimizes the input distribution. And in the example that I just showed to you, 0-1 sequence, with this correction probability, we can optimize this P and we find that the P that optimizes this is basically 1 over golden ratio to the square, and we obtain the result. Okay. So this is a mathematical result, but answers a question posed by Shannon, and we value it very much. But I could not finish without giving you something that, looking forward and trying to tell you that we need to actually go beyond sequences. The previous example were about sequences. I want to go to structures. So, and actually, Frederick Brooks in 2003, he wrote a paper, 3 Great Challenges of 50 years computer science, and he said the biggest challenge it is to extend Shannon beyond sequences and go to structures. How much information do I have a structure in a network, internet network? How much information do we have in a, let's say, organization chart of Purdue University? How we can answer this question? Okay, let me try to explain to you. On the left, I draw a connected few bubbles, which is called a graph. No labels here. And the question is, okay, how many bits do I need to describe it? That is a Shannon question, but not to sequences, but to structure. A more interesting question is, okay, let me put some labels into these bubbles. And actually, this label that I put are names, city names in Europe. Some of them are in the same country, France. This is Germany, this is Poland. Now, these 3 bubbles, they have different, the first part, but the same, the second part. They are locally correlated. The question is, how many bits do we need to describe this one? We have a postdoc who is actually working on this problem, but today I want to tell you a little bit about this. How many bits do I need to describe what we call unlabeled graph? Actually, the question is much more complicated than I tried to allude it before. This is protein-protein network seeing from afar. Connection between different, one enzyme, how it's becoming another enzyme, producing eventually a protein. Actually, if you look much closer into this, there is an interesting structure here which looks like a tree with labels. But actually, if you try to decipher this, you are going to a gene ontology that is another data structure that we call direct acyclic graphs with labels. So what do we have here? We have 4 different structures in one big data. And graphs, we have trees, we have directed acyclic graphs, and we have text. How to compress it? And actually, these are the real questions. Anand and I, we just got a grant from NIH, basically trying to find the best description of such a structure. Okay. Let's go to Greek letters now. So Let's assume that I tried to explain what we did. Let's assume we have 3 points on the plane, label. So I label them 1 to 3. How many different graphs, label graphs I can have it? You can see 8. But from the structure point of view, ignoring labels, I have only 4 structures. 3 isolated nodes, 1 edge, 2 edges, 3 edges. So I want to know how many bits do I need to a structure like this. So there are 2 entropies. Remember, entropy is the lower bound. I want algorithm that achieves this lower bound. Entropy of the graph, of the label graph, is relatively easy to compute. Entropy of the structure, I show you in a second, is not that easy to compute. But why? Because probability of this is actually probability of one of these times the number of graphs that falls into the same structure. Where the problem is? Problem is here. Look at this graph. It is a graph on 5 nodes with 5 labels. When I permute these labels, I put this A here instead of here, and so on. I permute all of these labels. I have 5 factorial, 120 permutations that give me the same structure. All of them are look like this. The problem is, what I told you is a lie. It's not correct. Because this graph has symmetries. This B and C and D and E view the whole graph exactly the same way. So if I flip B and C and D and E, I'm getting exactly the same graph. So the number of permutations that I need to get the same structure is 60, not 120. 120 divided by 2. In general, it is related to something what is called automorphism, the number of symmetries. This is a difficult problem. But we make some progress. So for special graphs, in which, another 5 minutes, in which we have the following, let's create a graph in the following way. I have n points. I pick up any pair, and I put an edge there with probability p, or not with probability 1 minus p. The probability of a label graph is giving exactly that when k is the number of edges. The question is, if I do this way, how much symmetries do I have? Others prove that for such a random graph, the number of symmetries is basically 1, which means that this graph is asymmetric. If it is 1, the log is 0, so basically I'm dealing with this. This tells us that the structural entropy can be computed this way. Let's look at these 2 terms. This grows like n squared entropy of an edge, entropy of P, minus n log n, then you have a term n and something else. This is an easy answer. A graduate student can do it. A difficult question is, can you give me an algorithm that compresses an arbitrary graph to the first 2 terms? Even the first term is easy. But 2 terms is a little more complicated, and I only show you some idea. So this graph, throw away labels, I don't have labels here, have this description. This is the shortest description that I needed. How do I do it? Basically, for every node in this graph, I store the number of neighbors. And I do something after that, and so this 2 string of bits store the number of neighbors in a special way. Then I concatenate them, do arithmetic encoder, and I get something. This is basically, this is irrelevant for most of you, for compression too, but it is important for me because I have to analyze this complicated structure in order to prove to you that if you do this way, this algorithm achieves what I wanted to do, achieves compression up to the first 2 terms. If you remember, these are the first 2 terms. I know that I cannot beat it, and actually I got these 2 terms. So this is a structure, an algorithm, that actually achieves the best compression up to the first 2 terms. So we do science, and we do also implement it, and actually this algorithm in particular, for several different graphs that do not satisfy Erdos-Chenier assumption, but that's a different story. But this algorithm is robust enough that actually if you can compare our algorithm to any others, it actually works very well from 20 to 40% improvement. And we have also science behind it. So that's what we try to do in the center. And we are going beyond the structure. We are trying to understand structure with labels and so on. Okay. At the end, I did not have time, but to tell you that all of these results were proven using a special technique. Most of these problems are discrete in their nature, discrete problems. But we use a very sophisticated technique of complex analysis, such as Mellin transform, saddle point method, Poissonization, singularity analysis, and so on and so on. Because, as Adamar once said, when he proved the number theory, the basic fundamental result of number theory, that the shortest path between two truths on the real line goes through the complex plane. When you go to a more complex abstract space, actually things are getting easier to understand. Okay, I'm basically done. First of all, again, I want to thank everybody, but this result did not have, I didn't do them. I did it with many collaborators around the world and with my students, and some of them who are listed here, I thank profoundly, because without them, I couldn't get even closer to where I am right now, and I'm very grateful to all of them. Thank you very much.